Hey everybody, I'm going to work some Hardy-Weinberg problems in this video. This is a topic that Matt covered in lecture, and I want to make sure everybody pays attention to how I assess your knowledge on this topic and some of the common little traps that students can fall into. So I'm going to adjust my microphone here. So let's get going. Once again, I'm recording this video from my palatial office next door to my nemesis, Dr. Neusmer, who keeps having meetings with people that are super loud. I advise you to take his class and give him a hard time about it in the spring, but next spring he's on sabbatical, working in Argentina. Anyway, so let's get to Hardy-Weinberg stuff. I set this up in Photoshop again, and that just allows me to write and change between layers and all of that kind of stuff. So, all right. What I've done is I've picked up. I can't remember when I did this a particular exam, but I chose this one. This is practice problem 1 that I've posted on BB Learn. Because I uploaded with this one an example of the formula sheet I used to use for these exams, and so I'm going to show you that by turning off these layers. So we'll deal with this this particular problem here in a second because it's a bleed over from a previous one. But this formula page. Most of these formulae we'll end up using on the next exam when we deal with quantitative genetics. The ones that are most relevant to the kinds of things that we've been learning for this unit are this, which you may or may not need. It's a Hardy-Weinberg equilibrium where one or more of the alleles are under selection. This formula right here, super important. This formula right here, super important. This one is potentially useful, and this one is potentially useful. So these two are must-know types of formula. Okay? So let's hide that for now and jump back to the question. So go to my answers layer and just try to map this out. I have an idea. Bring your calculator to the exam. I'll try to do these in my head, and then I will fail, and you can make fun of me later. But bring your calculator. All right, we have a Star Wars example. Some hard to pronounce little creature. Blah, 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 details, planets, doesn't matter. The phenotype that we're looking at is their ability to repel the force by creating a force-neutral bubble. Now, for those of you that are interested in the larger canon of Star Wars, I believe these creatures were first introduced in Timothy Zahn's series of novels that were set after the first Star Wars movies. They're really good. You should read them. Anyway, there's these creatures that can repel the force. Okay, so the ability to repel the force is conferred by the dominant F allele. So this is the first piece of information that's really critical to doing the problem. A rare recessive allele in these creatures interferes with the production of the bubble. So Grand Admiral Thrawn, who's total badass, collects 1,000 of these creatures and discovers that 18 of them cannot produce this bubble. All right, so the hardest part of these kinds of problems is converting this knowledge into the math that you must do to calculate the genotypic and allelic frequencies. The math is trivial. Converting the concepts, less trivial. All right. Now, chances are you've seen these kinds of things before in Biology 115. If you've already taken evolutionary biology, you've definitely already seen this stuff. If you've already taken Scott's population biology stuff, you've seen this before. That's okay. It's fine. Let's do it again. It's important. All right. What I'm really looking for is, do you know the difference between genotypic and allelic and phenotypic frequencies? Can you convert between them? Do you know what you have to assume in order to do that? And can you apply this knowledge to solve a particular problem? And then usually I'm going to ask you for the genotypic frequency of carriers in the population. Calculate the frequency of whatever, I don't even know how to pronounce these things, these creatures that cannot produce force neutral bubbles. So what we know is 18, handwriting. Let's see if we can zoom in just, oh my. It's a disaster. Okay, we're going to zoom back out. All right. Anyway, now we'll see if we can zoom in. That's better. All right. Sorry, that was a little distraction. 18 out of 1,000 of these creatures have this particular phenotype, right? 18 of them cannot produce. There it is. Okay. The frequency is therefore 0.018, and that is actually the frequency of individuals that have this genotype. See? A rare recessive allele interferes with that. Okay? So, little f allele. I don't think I ever say it in this problem. I'll have to fix that, but it says it right here. Right? So, the frequency of individuals with this genotype is 0.018. We've just earned ourselves 3 points. We're extremely happy. Next question. Oh, by the way, I've been helping a few students with these kinds of questions already, and one thing I've noticed is they want to do all of the stuff in part A, and they're like, well, now we have to calculate the square root, and we're going to do all this crap, and blah, 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 blah. It's like, no, calm down, relax. I'm going to ask you for that information down here. Stop jumping ahead. This is the answer to part A. Now I have to erase all of the crazy stuff you made me do. Look what you did. See? You guys stress me out with your stress. All right. Go back to the brush. 5 points. Calculate the allele frequency of the dominant and recessive alleles at the force repulsion locus. All right. Here's where we have to convert these numbers into our knowledge of how Hardy-Weinberg equilibrium works. And so if we know that the frequency of this genotype is equal to 0.18, we know that is equal to Q squared, right? So I could put this up here if you wanted to. So that means Q is equal to the square root of that should be 0.18. See, you made me do another typo again. Okay? It is not my day. Stop mocking me. Square root of 0.018. Now, do it in your head if you like. I tried to earlier today and failed miserably because I reversed the 8 and the 1. So, I have a calculator. Turns out these are really handy for the exam. You should bring one. Turning on a calculator. I'm going to calculate the square root of 0.018. It is 0.134. Okay? So, that is the allele frequency of the little f allele. One of the things that we need to know is P plus Q equals 1. We have two alleles in this system. The probability of one allele is 1 minus the probability of the other. So P equals 1 minus Q equals 1 minus 0.134. Can't write today. So let's use the calculator because apparently doing math in our heads is bad. 1 minus 0.134 equals 0.866. Yeah, I knew that. I knew it. 866 equals P. Okay? That really is sufficient for you to get 5 points, but if you want to be really thorough, the frequency of the F allele is equal to P is equal to 0.866. the frequency of the little f allele is equal to q, which is equal to 0.134. 5 points. Done. Again, math, super simple. Basic algebra. Mapping the numbers and the pros of the problem into what formulas and the mechanics you need to use, that requires practice. If you are not practicing these problems, I don't know what else to tell you. Please? Anyway. What is the frequency of carriers of the little f allele in the population? So, this is the application. Really, this example is sort of funny and trivial in a way, but this is actually important if we're interested in, say, a new rare genetic disease in a population and we would like to know the carriers, right? So, carriers are the frequency of heterozygotes. Now, some students think that carriers are also these homozygous individuals. Not really. Geneticists would call these affected, and heterozygotes are carriers. Okay? So the frequency of heterozygotes is 2pq. And now you're thinking, well, wait a minute, where did you get that from? Okay, so I'm going to jump back to the formula page. Here's what I'm using. P plus Q, I can't, blah, 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 target layer, okay? P plus Q equals 1. We used that. P squared plus 2pq plus q squared equals 1. These are the frequencies of the genotypes, the frequencies of homozygous dominant, heterozygotes, homozygous recessive. If you add them all up, they have to add to 1. So that's where I'm getting this from. Okay, let's come back to our question. All right, so the frequency of heterozygotes is 2pq. F's are a bad choice for alleles. I gotta stop doing that. Right? Which is nothing more than 2 times 0.866 times 0.134, because we calculated P and Q up there. Right? So you don't, I'm breaking this down for you. You don't need to do all of this in one step. So that is equal to, and again we'll do the math just to be sure of ourselves, 2 times 0.866 times 0.134 equals 0.232. All right, the frequency of heterozygous carriers in the population. Done. Okay, let's center this up a little bit. Now, that was an easy, not easy, but it was reasonably straightforward 14 points, 14% of the exam. I am going to ask you about the assumptions you have to make in order to do these kinds of problems. Now, the format for those questions is going to vary. Sometimes it'll be multiple choice, sometimes it'll be sort of mixed multiple choice like this is, and sometimes it'll just be list some assumptions or all of the assumptions. You've got to know the assumptions of the Hardy-Weinberg equilibrium. You can't graduate with a degree in biological sciences without knowing that. That's important. All right, so circle the Roman numerals of the statements that must be true. The intention here is for you to recognize that more than one of these could be true. In order for these calculations to be correct, we must assume that the population has sufficient heterozygosity. No, nowhere in Hardy-Weinberg theory do we have to assume anything about heterozygosity. That does not have to be true. 2, in order for these calculations to be correct, we must assume that the population is infinite in size. That is an assumption of the Hardy-Weinberg law, and so we would circle that. In order for these calculations to be correct, we must assume that the albinism locus is under strong over-dominant selection. All right, if you circle this, you may have an issue. 1, what is this isn't even about albinism. This is actually a leftover from a previous exam. Is under strong over-dominant selection, so we actually assume that there's no selection when we have to work with Hardy-Weinberg equilibrium, so this definitely must not be true. In order for these calculations to be correct, we must assume that the population is in Hardy-Weinberg equilibrium. Yes, absolutely. And then there's a 5th one that has hidden itself on the formula page. Sorry about that. In order for these calculations to be correct, we must assume the albinism is a meristic quantitative trait with high heritability. I tried to throw as many jargony terms at you as possible here. None of this is necessary or even relevant to the problem. You should leave that uncircled. Okay, so that is how to work a basic application of Hardy-Weinberg rules to calculate frequencies of genotypes and alleles. Hope this helped. If you have any more questions on it, you know how to get in touch with me, and definitely let me know if there are other videos or things that you need me to work that would be helpful as you prepare for the exam and you learn the material. All right, have fun studying. I'll see everybody in the test. Bye.